Hi again. This is going to be the last topic that will be part of the first test, and it's pretty simple, and it doesn't really use new deep concepts. It's just very simple. It's very quick to explain. Um, the key point here that I want to discuss is the distinction between what we call an ideal battery and a real battery. So when we draw this like this here in our circuit, this is called an ideal battery. What's special here is that when we say there's an EMF, let's say of 9 volts, we say that the difference of potential between this point and this point is 9 volts all the time, no matter what the rest of the circuit is. You can connect this battery here to several large resistors in series or small resistors in parallel or other batteries or anything else. You always get a voltage equal to the EMF. This is an ideal battery. Okay, so that's the definition. A battery is ideal if the voltage across its terminals is always the same no matter what it is connected to. So no matter what the rest of the circuit is. That's an ideal battery, always the same voltage. In real life, this is not what happens. Let's say you take a real physical battery and you connect it to a circuit. First of all, uh, and then let's say you measure the voltage here. Let's say you use a voltmeter. You connect here, and you measure the voltage between those 2 points here and here. First of all, you don't get exactly the value indicated on the battery. Let's say it says it's a 9 volts battery. That should be the EMF, but you don't usually get exactly 9 volts. Uh, okay, but it's close usually. So what? You might say, well, okay, maybe the value given here is not indicated on the battery. It's not very precise. Okay, but there's something more interesting. You take this exactly the same battery. Let's say you measure here, let's say 8.9 volts. You take exactly the same battery, then you connect it to, you change the circuit. So instead of having a light bulb here, you connect it to several kilo ohms resistors, and then you build a different circuit. And then you go back and you measure again the voltage between here and here of the same battery. You will get a different voltage than before. If it was 8.9 volts before, you might now get, I don't know, 8.65 volts. So the voltage across a real battery depends on what it's connected to. And that's a bit surprising at first. Okay, so just to repeat, if we measure the voltage across a real battery, we get a value slightly different than the EMF, and the voltage we get across a real battery depends on what it's connected to. So you change the rest of the circuit, you get a different voltage across a real battery. Why is that? So now we want to understand what explains that. And the basic answer is that when you take a real battery in the lab, for example, it contains actually a bit of resistance inside. So a real battery is actually equivalent to an ideal battery with a fixed EMF in series with a small resistance that we call the internal resistance. So we'll draw something like this. Now, just to be careful here, this dotted line here is not a wire. It's not part of a circuit. This is just something we draw here to encircle the real battery. So the real battery is actually this dotted box here. Inside there is an EMF, and which is really, this is an ideal battery in series with a small internal resistance R. The key point is that we don't have access to the inside. So I cannot use a voltmeter, for example, to go here and measure the voltage between here and here. That would be the EMF. I cannot measure that because it's inside. So we cannot access the ideal battery inside. The only thing we can measure is the voltage between, let's say, A and B. Those are the terminals of the physical battery. Okay, so we're only able to measure voltage across the terminals of the real battery, which is here in this figure, points A and B. The voltage you're going to measure between A and B is not equal to the EMF if there's a current flowing in the circuit. Because if there's a current flowing in the circuit, there's a delta V here, there's the EMF here, but there's also a delta V here, right? Given by Ohm's law, which is equal to R times I. So because there's a delta V here, the voltage you get across the real battery between A and B is not equal to the EMF. So the actual voltage you measure between A and B is what we call between A and B here, this voltage is what we call the terminal voltage of the battery. Okay, that's called the terminal voltage. So the question is, what is the terminal voltage of a battery? It's not equal to the EMF if there's a current flowing. So what is it equal to? Well, we have to consider two different cases. If the battery is discharging, so remember that means that the current is flowing out of the positive terminal and into the negative terminal. So here it's flowing to the right in this drawing. Now this is actual, it's not a guess, this is actual current for a discharging battery. Now we have that, we can assign the polarities. For the battery, well, it's minus and plus, as usual. For the resistor, it's plus here and minus here, because the current is going that way, to the right. Now that I have that, I can calculate the terminal voltage. Let's say we go from point A to point B. So as I go from point A to point B, I'm going this way. The voltage here increases by E. And then here, the voltage decreases by R times I. So the terminal voltage here for a discharging battery is given by the internal by the EMF, the ideal battery, minus the internal resistance times I. That's the equation. That's the voltage you're going to measure. And the key point about this equation is that the terminal voltage you get depends on properties of the battery, which is, what are the properties? The ideal EMF and the internal resistance. Those are properties of the battery. But also, what you get for the terminal voltage depends on the current, and the current depends on everything else that is in the circuit. So that means that the terminal voltage here will depend on what you connect the battery to, because it will affect the current, which will affect the terminal voltage. So that explains why the terminal voltage depends on what the battery is connected to in the entire circuit. Okay, what about a charging battery? If it's charging, then this time the current flows into the positive terminal. So here it will flow to the left. Again, now that I have the current, I can assign the polarities. Minus plus here, that's fixed by the battery here. For the resistor, this time I have a plus here and a minus here. Now let's calculate the terminal voltage again. So let's say I go from A to B. As I go from A to B here, the voltage is, well, the potential increases by E. And then here the potential increases again, because I go from minus to plus, by R times I. So as I go from A to B, I get a delta V equal to the ideal EMF plus the internal resistance times the current. So you notice the difference. When we add the discharging battery, we add the minus sign here. Okay, so that's the terminal voltage for a charging battery. Let's look at an example. Okay, this is a bit complex at first. Well, here you just, this dotted line here is just, again, to represent a real battery made of an EMF, an ideal battery connected with an internal resistance Ri. So they call it Ri instead of lowercase r. Maybe you might not be able to read the numbers here on the screen. So the internal resistance, little r, is 1 ohm. R1, R2, R3, they're all connected in series. They're given here, 2, 4, and 0.5 ohms. And the EMF of the ideal battery is 15 volts. Okay, if there's only one, well, you might not recognize the symbol here, but that's just same as having a long side here and a short side here like this. So here it's clear that the current, if there's a current, it will flow clockwise. Now here, this part here, this is not really part of the circuit. This is just a voltmeter. It measures the voltage. So this is just to measure voltage. It's like a DMM. And this is an ammeter to measure the current. Now there's a switch in the circuit here. The switch now is open. For now it's open. So because it's open, there's no current. There's no current flowing at all in the circuit. Now, because there's no current, then there's no voltage across the internal resistance. So if you measure the voltage you measure the terminal voltage between here and here, because there's no current, what you're going to get for the terminal voltage is written here is 15 volts, which is just equal to the EMF. So you get the full 15 volts. You get this here for the voltage across the real battery only when there's no current flowing in the circuit. So that the delta V in the resistor here is 0, and what you measure at the terminal of the real battery is just the EMF, 15 volts. Okay, now we'll take the same circuit, but we're going to close the switch. So we close the switch this time. Okay, the switch is closed here. This time there will be a current flowing, and it's easy to calculate the current because it's just a one loop here, and you just have resistors in series. The total resistance is 7.5 ohms, and the voltage, the EMF here is 15 volts. So the current you get is 15 volts over 7.5 ohms is 2 amps. There's 2 amps of current flowing in this loop here, okay, which is indicated here, 2 amps. Now, what's the terminal voltage? What's the voltage between here and here? This is a discharging battery here. So it's discharging. The terminal voltage is given by the EMF, which is 15 volts, minus the internal resistance times the current. So we get this. We get the terminal voltage is that's the EMF, minus the internal resistance times the current, and we get 13 volts. So we see that the voltage across the real battery is a bit less than the EMF because of the drop of potential across the internal resistance. So we get 13 volts. Okay. Okay. So a last example. I'll let you just try it. Okay. Again, this is here you have 2 real batteries here. One here is one real battery here, and that's the second one here. They both have internal resistance of 0.5 ohms. This one is a 4 volts, and this is a 8 volts EMF. Now, this one is pushing the charges this way because it's positive here, so it's pushing the charges this way. This one's pushing the charges this way. But now, because this is 8 volts and this is 4 volts here, the 8 volts will win over the 4 volts. So the current will flow clockwise. But you can just use Kirchhoff laws. If you don't see that right away, it doesn't matter. You can just apply Kirchhoff laws and you'll find the current. And the current here comes out to be, the total resistance is 24 ohms, including the internal resistors. You get 4 volts over 24 ohms, 0.167 amps. Even though the internal resistance are given with 2 sig figs, I'll assume that they're really 0.500 to keep more precision. So the current is going clockwise in that circuit and given by this. Now you can find the terminal voltage across the 2 batteries. The top battery here, the current is flowing this way into the positive terminal, so it is charging. So we use the EMF, which is 4 volts, plus internal resistance times the current, and if you do the calculation, you get 4.08 volts. So the terminal voltage is a bit more than the EMF, which is 4 volts. And that happens when the battery is being charged. The terminal voltage is higher than the EMF. For the bottom battery here, this one is discharging. So for this one, the terminal voltage is the EMF minus the internal resistance times the current. And this time you get a bit less than the EMF for the terminal voltage of the 8 volts. Okay, so that's it. So that's how you find the terminal voltage of a real battery. Thank you.